Hello everyone, welcome to the NPTEL online certification course on fundamentals of food process engineering. So, we were discussing with the property of the fluid food in the last class. We will continue with different non-Newtonian behavior. Okay. So, in the non-Newtonian we have discussed the pseudoplastic and dilatant flow behavior, which is termed as shear thinning and shear thickening behavior. Now, in this particular class we will first see the plastic flow behavior. So, what is plastic flow behavior is that some kind of material will need some initial stress value before they flows. Okay. So, the initial stress, that is tau 0, is required to cause flow in this kind of a material, but when they start flowing they will follow the linear pattern. Okay. That means, again the slope of the shear stress versus shear strain diagram will be constant, and one property will enough to explain their flow behavior in this region, that is called the plastic viscosity, and this tau 0 which is called the yield stress. So, this kind of flow behavior is termed as Bingham plastic behavior. Okay. So, fluid will not begin to flow until a minimum shear stress is exceeded, and this minimum shear stress is called the yield stress. So, for an example we can see the toothpaste, where we need to put some initial stress, then only it will squeeze out. So, flow will start. So, this kind of material we can express by the equation tau y z, that is equal to tau 0, that is the initial stress or yield stress required to cause the flow, plus k into dVz by dy. So, k the consistency index and dVz by dy is the shear rate. Okay. Now, if we try to analyze the apparent viscosity in this case, where apparent viscosity is a function of shear rate, that is equal to shear stress by shear rate. So, stress will be tau 0 plus k into gamma dot divided by gamma dot. So, that is equal to tau 0 by gamma dot plus k. So, the intercept on the stress axis at 0 shear rate, okay, this is the yield stress, and in this region, since we can observe that although we are putting stress, there is no change in the strain. Okay. So, that means the viscosity is mathematically the derivative of the flow behavior curve. So, the yield stress on the viscosity curve appears to originate as an indefinitely high viscosity. Okay. So, this shows the indefinitely high viscosity, and because of this no flow we can observe. Okay. So, viscosity is actually to resist the flow. Then we can see that for the non-Bingham plastic fluid. So, Bingham plastic fluid, that means the fluid which follow the Newtonian law, but they need some yield stress, but non-Bingham in the sense they will also need an yield stress, but when they starts flowing they does not follow the linear pattern like the Newtonian fluid. Okay. So, if we plot that shear stress versus shear rate, the curve will be a non-linear, and in this particular case it is again showing a shear thinning kind of a behavior. So, this kind of phenomena can be mathematically expressed as Herschel-Berkeley model, that is tau y z, this is equal to tau 0 plus k into gamma dot y z to the power n. The example will be minced fish paste and raisin paste. They obey the Herschel-Berkeley model, and flow behavior of the rice flour based batter, because sometimes we use the rice flour based batter for preparing different snack item. or the fried products. So, they will follow the Herschel-Berkeley model, that means the non-Bingham plastic behavior. Now, another model which is called the Casson model. Casson model will also show the non-Bingham plastic nature of the food. This is shown as tau yz to the power 0.5, that is equal to tau 0, that is the yield stress to the power 0.5 plus consistency index into shear rate to the power 0.5. Especially this kind of phenomena has been found in case of molten milk chocolate. So, then we will consider the fluids which are time dependent. So, till now we have considered the behavior which are time independent. So, their viscosity will change on the rate of shear, but does not change with time. But now we will consider certain non-Newtonian fluid which will also show different rheological behavior with time if the shear rate is constant. Okay. So, first one that we will consider, that is thixotropic flow behavior. So, in case of thixotropic flow behavior, if we apply a constant stress, okay, a constant shear rate is constant, then also the stress is decreasing or the viscosity will be decreasing. And another flow behavior is there where we are getting just the reverse trend, that at constant shear rate with increase in the time, the shear stress is increasing. Okay. However, for the time independent fluid like Newtonian fluid, we are getting that there is a constant shear stress with respect to time for a constant shear. Okay. So, the shear stress or viscosity that decreases over time at constant shear rate, this is caused by a decrease or breakdown in the intermolecular interaction within the molecular structure of the material. For example, gelatin, egg white and shortening. Now, here also we can offer we can see this kind of behavior like true thixotropy and apparent thixotropy. That means, the material which show decreasing nature of shear stress at constant shear rate over time, and when we when we want to show the effect of the I mean when we want to change its force or the shear rate and bring it to the initial condition, then its viscosity will be recovered, then we termed it as true thixotropy. But if its structure has been changed completely and initial condition cannot be regained when we have removed the shear stress, then we can call it apparent thixotropy. So, thixotropic behavior, that means may be reversible, partially reversible or irreversible when the applied shear is removed, right. So, fluid is allowed to be at rest, and with time we can see this behavior. So, irreversible thixotropy is also called rheomalaxis or rheodistraction. So, what happened that with time, if at constant shear rate we apply and the stress is gradually reducing, then at certain time if we rest it at that position. So, what happened that the some material can completely recover that if the shear is removed, and those are called the reversible, and some may partially can gain the initial structure, those are called the partially reversible thixotropic behavior, and some material where they cannot regain at all. So, they will just whenever we again apply shear, they will start from that point only where it has already reached when the stress condition. So, these are the nature. Now, so shear stress versus shear rate curve if we plot in case of this kind of a material, as the shear rate is first increased, okay, as the shear rate is increased towards this direction and then it again decreased, we will get a hysteresis loop. Okay. So, here in case of thixotropic behavior, we can observe that when we have increased the shear rate, the curve that we will get, and when we decrease the shear rate, there will be certain change. So, this change happened because of some change or some permanent deformation that has happened in the structure of the material. Rheopectic behavior, which is just reverse of the thixotropy, that shear stress and apparent viscosity increases with time, that is the structure builds up and as the shearing continues. For example, bentonite clay suspension, it is rarely observed in food system. So, example is fenugreek paste, this exhibited the rheopectic behavior. Okay. So, at a constant shear rate, if time increases, shear stress and viscosity increases. So, this happened because of some kind of interaction, molecular interaction between the product, and it has increased its viscosity over the time. For example, the starch, milk and sugar paste. So, pasting process can happen at 85 and 95 degrees Celsius. This exhibited a thixotropic behavior. However, pasting at 75 degrees centigrade behave as a rheopectic fluid. So, here temperature is a factor that is causing some change in the material property, and because of that the structure has been thickened or the viscosity has been increased. So, it was noted that the thixotropy occurred at high shear rate, that is above 50 Pascal, and the rheopexy occurred at low shear stress below 45 Pascal. So, all such food material, they are very specific kind of nature, because there is no generalized way of that, because processing has been done in different pressure, different shear, different temperature, different duration of time. So, all such are the research based on the research based results, and there are certain modeling has been developed for these different material, and from where we can gain this kind of inferences. For example, when soy protein was added to tomato juice, thixotropic behavior was observed at low shear rate, but this was followed by a transition to rheopectic behavior at high shear rate. Okay. So, thixotropic, that means viscosity was reducing with time at a constant shear, and just reverse trend we are getting when the when we just increase the shear rate. Okay. So, whenever we perform any kind of industrial process for product development, and so we need to therefore very much aware of the all the rheological nature, because when we mix and then we see the different fluid line or the different capability of the pumping and all will be changed based on this nature of change of the material. Therefore, the rheological understanding of the product that we want to make in a processing plant is very important to assess. So, on the whole, if you can see the classification of rheology, so rheology can be termed as can be categorized into two broad category, deformation and the flow. So, the flow is basically the property of the fluid that will show continuous deformation over time, and it can be categorized as plastic and viscous material. Plastic material that needs an initial stress to flow, that means initially they show the infinite viscosity unless they reaches the or they exceed the yield stress. So, there again Bingham and non-Bingham nature. Bingham means those material which show the Newtonian behavior when they attain the yield stress, and non-Bingham when they does not show the Newtonian behavior when start flowing. Viscous, they may be Newtonian and non-Newtonian. Newtonian, they will follow the Newton's law of viscosity, that is linear relation between stress and shear rate. Non-Newtonian, that means this material, this fluid will does not obey the Newtonian behavior, neither they will pass through the origin, they will follow the power law equation. Okay. Then from the deformation we can categorize them elastic and inelastic material. Elastic material follow the Hookean deformation or non-Hookean, whereas inelastic is viscoelastic and viscoplastic, right. So, viscoelastic, that means they have possess both the property of the viscous material, that the fluid behavior, and plastic nature, that is they need some yield stress to flow. Viscoelastic, this is very important in terms of food. We will eventually discuss in our later class regarding this, because most of the food items comes under this category, viscoelastic. For example, your dough and many kind of batter or mix. Okay. So, this will possess the viscous property as well as the elastic property. That means, they have some quality, because of that they can regain its initial behavior partially. However, some deformation will happen, that is a permanent deformation that cannot be recovered. Okay. So, this is all about the overall classification of rheology. And lastly, there are many rheological functions are there, mathematical equations that describe the various flow behavior curve on shear stress and shear rate diagram. So, rheology of the fluid, if we consider, rheological models can be grouped into three categories: empirical, theoretical and structural. Empirical in the sense, when we plot the shear stress and shear rate diagram, and we prior does not have any idea about what is the structure. So, we can't do any modeling unless we get the trend of their change of shear stress, and from that plot what we are getting, we can derive or we can generate certain kind of a model. So, we term them in empirical model. Theoretical means that derive from the physics based principles that already we know the physical expression or the relation between the stress and strain. So, from that we can categorize these models. Structural models, this based on the internal structure or the composition of the food. Okay. So, all three kind of models are available for analyzing the rheological behavior of different food sample. So, we will stop here. Thank you.